There's this image of the sun going around on the internet. This is what it looks like. But there's a catch. The image was taken at night. How do you think that's possible?
Oh, wait. Taken at night?
Yes.
Oh
from
my
the
God.
surface of the Earth.
And you can't pick it up with visible light. Is it like infrared or something else? Like,
No.
we are not picking it up. Oh, via light in any form.
Not light. No.
I don't know. What else comes off the sun that we can detect for?
You're on the right track. Okay, something from the sun that goes through the Earth.
I don't know.
Have you ever heard of neutrinos?
I've heard of them.
Yeah, okay. This is made with a giant detector in Japan called Super Kamiokande.
Oh, cool.
That detects these particles called neutrinos. This is an image made by detecting a bunch of neutrinos from the sun. People have often never even heard of neutrinos, but yeah, about 100 billion solar neutrinos are passing through your thumbnail every second.
Crazy.
Which is wild. Okay, but pause. I want to tell you something crazy about how elusive neutrinos are. Like, maybe the most elusive particles in physics. Guess how long it takes for light to get from the center of the sun to the outside of the sun?
Oh my God. Can I guess?
Yeah, of course. I always want you to guess.
Less than 30 seconds.
That's a great guess.
Yeah.
Okay, so if it were traveling straight, not interacting with anything, it would take about 2 seconds for light to get from the center of the sun. Order of magnitude, you're on.
Nice.
If it weren't interacting with anything. But the sun is extremely hot and dense, which means that there's a lot of matter for the light to interact with. So therefore, when light's produced in the core of the sun, to get to the outside of the sun, it actually takes, you ready for this number?
What?
Hundreds of thousands of years.
What?
Yeah.
Seriously?
Hundreds of thousands of years. Because light is actually, it's not going straight. It's like bumping into this hydrogen molecule, this helium molecule. Because in between all those interactions, it actually is going the speed of light. So like this, for example, the speed of light in water is not the speed of light. It's the speed of light in water. It's actually a little bit less because it interacts with water molecules along the way. Guess how long it takes neutrinos?
How long?
It's 2.3 seconds.
Oh my God.
Because they interact with matter so little. So light interacts with matter quite a bit.
So light takes hundreds of thousands of years to get to the surface, and then it takes 8 minutes to get to us.
8 minutes to get to us.
The neutrinos we can see right now happen so much sooner than the light we're seeing, like when it was created.
Exactly.
Yeah.
So if there was like a solar apocalypse or something crazy going on in the core of the sun, we would find out from neutrinos. So they would be like our blinking solar apocalypse signal. Neutrinos are known as the ghost particle because they'll just pass through a wall like a ghost. They'll pass through the entire Earth like it's nothing. So you'd think this image of the sun maybe shouldn't be possible. So then how is it possible for us to detect these particles, these ghost particles, if they're going straight through the sun essentially, and then they're going straight through the Earth? Like, why would you detect them in your particle detector? Well, you just need lots of them, like lots and lots of them, because they do interact. They just interact really infrequently. Guess how many neutrinos get detected in the Super Kamiokande detector every day?
Every day. 500,000.
Good guess. It's 30.
30,000?
30.
30? That's it?
30.
Whoa.
Which is why the image is so blurry, even though they spent 500 days detecting, because you barely get any neutrinos.
Do they have a reaction on us?
Yeah, every once in a while, just like in the detector, they'll like knock an electron and
Really?
Yeah. They have very little mass, so they're gonna just kind of like boink the electron. They are going very fast, so they actually do have quite a bit of energy.
It's happening right now? Like
Yeah. The picture that I showed you, this picture wasn't actually taken fully at night. It was actually taken over the course of about 500 days. So it was night and day. It was actually taken deep underground. So it's about 1 kilometer underground. That's where the Super Kamiokande detector is located. That's one of the other ways that you get enough detections in order to make an image. And it's still a pretty blurry image, but yeah.
So there's trillions coming through every second, but they spend 500 days?
Yes.
Like absorbing neutrinos or whatever the term is for what they're doing.
But this detector is really big. It's this giant cylindrical tank that's about 40 meters by 40 meters. All the pictures of it are when it's empty, but it gets filled with water. It's 50,000 tons of water. And then these light detectors all around in the water. So what happens is the neutrino comes in, it kicks an electron, that produces a flash of light in the water, and then these light absorbing detectors will detect that very tiny flash of light. And that's how you see a neutrino. Even though neutrinos are one of the most mysterious objects in the universe.
So then what is a neutrino?
What is a neutrino?
Yeah.
It's like I said, it's a subatomic particle. One thing that I didn't know is that not every particle interacts with all of the forces. So there are 4 fundamental forces: the electromagnetic force, gravity, electroweak force, and strong nuclear force. And neutrinos only interact with 2: gravity and the electroweak. You don't really need to know that, but you have to know that.
I like knowing, yeah.
You like knowing it?
Yeah,
Okay,
I like hearing about it in this context.
So neutrinos are basically the perfect particle for this, because they're subatomic particles that barely interact with other mass because, one, they themselves have very little mass. We actually don't even know their exact mass, but we do know it's at least 1 million times less than the mass of an electron. In fact, we thought that they were massless until 1998, when there was a discovery that neutrinos have a tiny amount of mass, which won the Nobel Prize in 2015.
Really?
So these are like recent physics.
Super recent.
Yeah. Some of the big unanswered questions about neutrinos is, how massive are they really? Another is, are neutrinos their own antiparticle?
Oh.
Like, for example, the antiparticle of the electron is the positron. What is the antiparticle of a neutrino? We still don't know. So that's exciting. Are there new dimensions or forces that we can find using neutrinos? Maybe. They're a ghost particle, but they're kind of like your uncle as a ghost, like kind of tapping your shoulder and being like, there's still more to learn about the universe, but it's just lightly tapping your shoulder for decades, and maybe someday we're going to get to a place where we learn those answers.
How is the scientific community reacting to that photo? And
this photo is from the 1990s.
Wow.
Yeah, it's old. Levi, first physics video in 3 years.
First physics video in 3 years.
This is so exciting.
Back, physics girl. We're starting strong and doing neutrinos. This is a cool topic.
Clapping for myself.
Working from the bed,
yeah,
as you have to with long COVID. Yeah, we're deciding to stop now after filming for about 15 minutes because you're already feeling your energy drop a little bit.
Yes.
Yeah,
I'm feeling a little dizzy. I'm feeling like as time is going on, you're asking questions, and more I'm looking at you like what languages he's speaking.
Oh, cut, but this is really cool that we get to film again.
I know.
Yeah.
You have no idea how excited I am.